The last talk for the day, Martin Hara on the renormalisation group landscape in 1+1 dimensions.
Okay, thanks. Thanks to the organizers for the invitation. Yeah, so this talk, it's about 1+1 dimensional systems, so meaning one space, sorry? Oh yeah, sorry. I forgot to turn on the mic. So one space dimension, one time dimension, okay? And so the kind of models we're interested in are models with the following features. So basically you have some evolution, right? So you have a time evolution of some height function, h, which would be a function from, say, r to r. And you want your time evolution to be local, right? So not necessarily local in an absolutely strict sense, but somehow, you know, the way it evolves, the rule for evolving h at some location should only depend on h in some kind of neighborhood of that location, or maybe the dependency should decay, you know, sufficiently fast as you go away from that neighborhood. So it should be local in that sense. It should be stationary in the sense that, you know, the rule for your evolution shouldn't depend on where you are, neither in space nor in time. And then it should also be vertically translation invariant. Okay, so vertically sort of shift invariant in the sense that if I just add a constant to h and then let it evolve, it's the same as first letting it evolve and then adding that constant. Okay, so in some sense, the rules for evolving h only depend on the local shape of the function, but they don't actually depend on the absolute height of the function, right? So if you take the same function, you shift it up, it's going to evolve in exactly the same way as if it were somewhere down there, okay? So it doesn't see where it is vertically either. So what's the typical rules for that, right? So a typical rule for that is this one, for example. So this is ballistic deposition. Okay, so ballistic deposition is the following rule. So here your height function is if you want at every, so here it's just a function from integers into integers. At every location, the value of the function is sort of the location of the highest brick, if you want. And the rules for these bricks, the rule is that you choose a site at random. So say you put a Poisson clock on every site, and then when the clock rings, you have a brick falling down, and then it just stops wherever it can't move anymore, but it also sticks to neighbors, right? So that's why you create these overhangs, because if there's a brick sort of falling down, you know, somewhere here, they can stick to the neighboring bricks, right? So it can kind of grow sideways and not just up. And what you're interested in is, of course, the large-scale behavior of these things, right? So you're interested in figuring out how this thing behaves when you zoom out. And so it sort of looks like this. And so, right, so here you see it looks like there's some kind of continuous limiting random curve, right? And you want to have some kind of understanding of that random curve. Right? And so what you'd like to do is, in particular, you know, ideally, you would like to characterize all possible sort of scaling limits that you obtain from models of that type, right? So another example of a model of that type is sort of what's called sometimes, well, simple exclusion process, the height function for a simple exclusion process. So now your height function is again a function from integers to integers, But this time it has the additional property that it only ever varies by exactly +1 or exactly or -1, right? So it's sort of like a simple random walk. Okay? And now the time evolution is that local minima can turn into local maxima, and local maxima can turn into local minima. And well, if it's locally straight, then it doesn't move. Okay, and so again, same thing. So you just put a Poisson clock at each side. If the clock rings, it looks at the shape of the function. If it's a local maxima, it turns into local minima. If it's minima, it turns into maximum. If it's locally a straight line, it does nothing, right? So if you simulate that, you get something like this, right? So that's now the. It looks somewhat similar to the previous one. So for example, so the conjecture is, okay, so no. So a theorem is that this is really different from what, well, no, so that's still a conjecture because ballistic deposition, there's basically no theorem. So conjecture is that what we see in this movie is actually different from what we saw in the previous movie, but they look somewhat the same. So in the sense that what we are supposed to see in the previous movie was this. Now, you can spot the difference. There is a difference. Okay, so what is being simulated here now is essentially the same dynamic as that, but the difference is that you actually, when the clock rings, if it's a local minimum, you always flip it into a local maximum. But if it's a local maximum, you turn it into a local minimum only half of the time. Okay, so it has more chance of going up than of going down. And then, of course, the whole thing is going to kind of fly upwards, so you recenter it so that it stays centered, right? And then what you see is this, which is conjectured to be the same as what you would see for the large-scale behavior of ballistic deposition, but there's no theorem. Now there is actually, okay, so if I switch, right, so here there's a switch I can turn on and off, which makes it either symmetric or asymmetric, which is supposed to switch between the two scaling limits. And if you know what to look for, you actually see the difference in the dynamic. So you cannot tell the difference if you just look at the snapshot. In both cases, as a function of space, it's just a Brownian motion. Okay, so you can't tell the difference by snapshots. You really have to look at the movie. But here, so this is sort of the symmetric case. In some sense, fluctuations only go sort of up and down, whereas in the asymmetric case, I'm going to switch it in a second. If you look for it, you kind of see fluctuations going sideways. So in a way, you see if I switch now, it sort of looks more wobbly, right? And you see things sort of moving, right? So when you have sort of fronts like this, you actually see them moving sideways. Things sort of tend to move outwards. Whereas, right, yeah, so that one looks more interesting, right?
Well, but
so
it's because you are recentering it, so somehow it is. No, it's just growing everywhere, and if you
it's growing everywhere.
It looks like going ways, but
yeah, but it grows more, right? So in some sense, you see, so what it does is you sort of imagine that it kind of grows in the normal direction of the surface, right? So in some sense, it's closer to something like that, whereas in the other case, it was really just purely vertical kind of fluctuations, okay? So the picture here is that, okay, so we have two, all right, so far the picture is the following. So we have, so under the operation, sort of the RG picture, sort of the operation of zooming out, if you view that as a sort of dynamical operation, you have two fixed points now. So there's one of them called the Edwards-Wilkinson fixed point, and Edwards-Wilkinson is the one corresponding to the symmetric case. So that will be this one. And then there's another one called the KPZ fixed point. That's the one which you're supposed to see when you switch. No, so that's symmetric, sorry. Okay, so that's Edwards-Wilkinson. That one is supposed to be KPZ, or what we saw in the case of ballistic deposition. That's supposed to be this KPZ fixed point, right? So both of them, so what sort of properties do they have, right? So they should still reflect some of the properties that we started from, right? So this locality turns into, right? So here I said, well, they should be essentially local, the dynamic. Now, by the time you've taken a scaling limit, essentially local becomes exactly local, right? And so exactly local here means that it's actually space-time Markov. Right? In the sense that these are processes on space-time, and space-time Markov means essentially if you take a chunk of space-time, so say you have your x, you have t, say I take a curve in space-time, but it doesn't have to be a horizontal line. So the usual Markov property would correspond to taking a horizontal line. So you take an arbitrary curve like this, you condition on everything that happens below the curve, you look at what happens above the curve, conditioned on that, it depends only on what happens on the curve, right? So that's the, if you want, Markov property, but in space-time. So you have that space-time Markov property, and, well, you keep stationarity, you keep shift invariance, and of course you pick up another property which is scale invariance, because you got these processes as a scaling limit, and therefore, you know, if you get a limit by zooming out, then that limit has to be invariant under the operation of zooming out, right? So they are scale invariant, and they're scale invariant with different exponents. So Edwards-Wilkinson is scale invariant with exponents 1, 2, 4, and what that means is that h of tx for the limiting guy is the same in law as lambda to the minus 1 h of lambda square, well, I should have written xt, lambda square x lambda to the 4t. Okay, so the correct way of scaling things is to put the ratio of these three exponents should be the same ratios between 1, 2, and 4. Oh, you can't see what's written there. Okay, so I wrote lambda to the minus 1 h of lambda square x lambda 4t is the same in law as h of xt, you know, as a space-time function of x and t, not just for fixed x and t. Right? So that's for Edwards-Wilkinson. And for KPZ, a similar property would be true, but the exponents are 1, 2, 3. Okay, so instead of having a lambda to the 4 here, you'd have a lambda to the 3 here. Yes?
The first model, it was not clear where you get the graph. These bricks could have somehow overhangs, or did I miss out?
That's right. Yes, they do have overhangs, but then the conjecture would be that by the time you look at really large scales, these overhangs, you don't see them.
All right.
Yeah. So you would get a continuous function in the limit. Okay.
Why is Markov property replaces locality? It's not obvious to me that it's local, because just you move one tiny epsilon in time, but you still allow dependence everywhere along the surface. So why is this local?
No, so I don't. A second. So here I wanted local rules for updating. So I wanted. Yeah.
When you say Markov means exactly local, it's not clear to me why you call it exactly local. Because you say I'm going to allow dependence everywhere on the value of the field in the future depends on everywhere along.
No, but that's the point, is that you want, so in the limit you get the space-time Markov property and not just the usual, right? The usual Markov property would be a locality in time, but it doesn't say anything about space, because the usual Markov property is only something about time, right? So as these guys have the space-time Markov property, and so there the evolution is really local, if you want, in space and time, not just in time. Okay, so if it only had the Markov property, you're right, that doesn't tell you anything about spatial dependency. It could depend on as far as you want, okay? But the space-time Markov property, that one tells you it's some form of locality, really. So now you would like to, you know, like you ask yourself, so for example, you can ask yourself, questions about the stability of these things, in the sense that, you know, how big are their sort of universality classes, right? So, like, if you take an arbitrary process with, you know, these sort of properties, so typically when you zoom out, you know, is it going to converge to that guy, or is it going to converge to that guy? Right? So like, which one of them is sort of more stable? So one thing that you can see is that this guy has more symmetries than that one. So that one, there's an explicit description, so it's just stochastic heat equation. It's an explicit Gaussian process, which is very easy to describe. And it's symmetric. It has 3 symmetries. So that one is symmetric under x goes to minus x, t goes to minus t, and h goes to minus h. So it's under all of these 3 transformations, you get exactly the same guy back. Okay? This guy is symmetric under x goes to minus x, and it's also symmetric under simultaneously mapping t to minus t and h to minus h, but not separately. Okay, so if you just map h to minus h, you get the same as if you map t to minus t, but you don't get the same process back, right? So this guy has, if you want, less symmetries than that one, you know, which sort of suggests that it's a bit more generic, right? So what actually would happen is that typically, well, if you start from a model, you know, a discrete model, which has all of these 3 symmetries, well, then chances are that it's going to converge to that guy. If you start from something more generic, which doesn't really have any symmetries, well, it's more likely that it converges to that guy. So the picture here is, if you want, this guy is sort of very stable, and this guy has some unstable direction, right? So now you can ask yourself, well, so what happens if you follow the unstable direction, right? So here the conjecture would be that you follow the unstable direction, it kind of leads you to that guy here. And so what does this line correspond to? So this line would correspond to the KPZ equation. Okay, so if you want a precise way, so here you could formulate a precise mathematical conjecture which would say that the KPZ equation is the only continuous space-time Markov process which has the property that if I zoom in under this scaling, it converges locally to the Edwards-Wilkinson. So you zoom in and recenter vertically, you converge to the Edwards-Wilkinson model, and if you zoom out under this scaling, you converge to a KPZ fixed point. And so there the conjecture is that there's exactly one. So there's that this heteroclinic connection, if you want, between these two is just one-dimensional. So there's exactly one process, if you want, that interpolates between these two in a natural way, and that's the KPZ equation. Yes?
Am I supposed to understand why there can only be 2 fixed points? Couldn't there be more?
Right, so there could be more. So I'm going to show you a third one. Yes?
Martin, so is there something like a temperature that you have to fine-tune, or if you...
No, so here there's nothing like a temperature. There's nothing like a temperature. In some sense, I mean, so here, this guy would have to have sort of quite a bit of symmetry. So in some sense, the thing that you would tune is more like the asymmetry. Right? So like 0 asymmetry would lead you to this guy, right? And then as soon as you tune it away a little bit, it would lead you to that guy. And so, right, so then that would be, so one way, if you want a weaker form of the conjecture that I just mentioned, the one about KPZ equation being the only space-time Markov process with these two properties, slightly weaker form is the following. So you take some model here, which is actually symmetric, so that guy converges to Edwards-Wilkinson. Then you slightly perturb it, you make it slightly asymmetric, you zoom out, and then what you expect is that, you know, if you tune the asymmetries, you sort of send the asymmetry to 0, but you simultaneously zoom out sort of at the right scale, then you end up somewhere on that heteroclinic orbit, and so you end up seeing the KPZ equation, right? And so this is, well, of course, the result by Bertini-Giacomin is exactly of that type, right? Which says you take the symmetric simple exclusion process, you add a weak asymmetry, you zoom out, you look at the right scale, it converges to the KPZ equation, right? So that's exactly a result of that type.
Why you are saying there is no temperature? You can easily introduce it. You can somehow create some overhangs with, somehow.
I think the point is
the point is that it doesn't play any role somehow.
the vertical shift invariance basically removes that. No, it's like a gradient model.
Mm-hmm.
Because you're enforcing vertical shift invariance, it's a gradient model, so it's always in the. If you remove that, you probably get white noise as a limit as well.
Right. Yeah. Mm-hmm. Well, so here you can get white noise if you just have bricks falling down and just piling up without sticking to neighbors, then of course you get sort of Brownian motion in time and white noise in space, which I suppose would be a third point here, but that's really not an interesting one. So I don't really want to discuss that one.
I guess the question is, like, does that fixed point EW has any other? You said that if you demand the preservation of the symmetries on the left, there is only one operator which perturbs. But there are other symmetries that we might want to break, and if there is any other perturbation of that kind.
Right. So the thing is, so if you break the translation, the x goes to minus x symmetry, what typically happens is that you, in some sense, you actually get back to the same. No, okay, not here, but so here in the KPZ fixed point at least. So here, if you break the x goes to minus x symmetry, in some sense, you actually get back still to the same fixed point because there's a sort of Galilean transformation you can do, and it has some invariance under that somehow. Right, so in a way, that breaking the x goes to minus x typically doesn't really get you far from this picture. Now, okay, so you can ask yourself, what are sort of other natural models where you can sort of tune the asymmetry? So one thing we wanted to do, so this is joint work with Giuseppe Cannizzaro, who is a postdoc with me at Imperial. And so what we wanted to do is we wanted to find some sort of nice perturbation, if you want, of the ballistic deposition model. Right? So the ballistic deposition model, well, that's the one we saw the previous simulation, right? So there was that one, right, so with the bricks here sort of piling up, there are very few results. There's essentially almost no mathematical theorem about that model. And so what we wanted was to find, a natural one-parameter family of models here, if you want, where, well, there's one guy which would be a symmetric one, and then there would be something like a temperature or some parameter that connects this in a natural way to ballistic deposition. And so that, if we could then show that the weak perturbation of this guy also converges to the KPZ equation, that would at least indirectly give some sort of reasonably good evidence that ballistic deposition is really in the KPZ universality class. Right? So the the model that Giuseppe came up with is the following. So what he said is what you could do. Okay, so I'm running out of space, but I'm going to remove that screen soon. So ballistic deposition is the following evolution, right? So you have these bricks falling down, and so the new value of h, so if clock rings at a site x, so the new value of h at x is the maximum between current value plus 1, which corresponds to the brick just falling all the way down, or the value at the left, or the value at the right? So you look at h of x plus 1, h of x minus 1, and h of x plus 1, and you take the max between these three values, right? So can you turn on the projector, please? And so what Giuseppe said, well, one thing that we could do is instead of taking the max of these three values, we could just pick one of the three at random. Right? So that would be in some sense like an infinite temperature version of ballistic deposition, where ballistic deposition itself would be the zero temperature version. Right? And you could take a finite temperature version where you just bias by the height. So if you want, you pick the new value between these three with a probability which is proportional to e to the beta times the new value, right? And then beta equal to infinity can you, oh, okay, thanks. Beta equal to infinity then would be ballistic deposition, as beta equals 0 would be some sort of like an infinite temperature version of ballistic deposition. And so then when you simulate that, so that's now the beta equals 0 version of ballistic deposition, where the new value, instead of just being the max between value on the left, value on the right, and current value plus 1, you just pick one of the three values at random. Okay? And so now you can zoom out this. So it looks like that. So now clearly that one is actually neither one of the two that we've seen before. Right? For starters, it doesn't actually look like it converges to a continuous function. Right? It looks like it converges to something discontinuous. Well, so, you know, as Jörg said, well, there's no reason why there should be only two fixed points, so there's a third one here. Right, so now we have a third renormalization fixed point, which is this. Okay, so which we call, okay, so we call that the Brownian castle because, you know, it forms these kind of towers. So can you know, can we have a description of this guy here and how stable, you know, how does it relate to this picture? So first you can actually figure out, I'm going to show you in a second there's an explicit description of this object. So it actually has quite a nice, in some sense it's a free fixed point in the same, but in a it's different from Edwards-Wilkinson, of course. And so it's scale invariant with exponents 1, 1, 2. And so here you see the first two exponents are the same, so it's 1, 1, which means that the height scales in the same way as space. And right, so that's why when I sort of zoomed out, it didn't flatten out, right? So in the other picture, in the ballistic deposition picture, it actually got kind of flat. Here it doesn't get flat, right? Sort of like the height of these towers is roughly the same as the distance between towers, right? So it's you have the same scaling horizontally and vertically. So now you can turn off the screen, please. Okay, thanks. So what is this object? Well, remember, so the construction was that you map, that you have independent Poisson clocks at every site. When the clock at site x rings, then you map h of x into either h of x plus 1 with probability a third, h of x plus 1 with probability a third, and h of x minus 1 with probability a third. And so there's actually a very nice graphical construction of this. So what you do is so you put your space here, you put your time here, okay, so that's x if you want. So now at every site, so you put a vertical line above every site, and now what you do is you just throw down a Poisson, or if you want, 3 independent Poisson processes, each of them with intensity a third, and at every event of the first Poisson process, you draw an arrow to the right. So you have sort of arrows to the right that get thrown down according to some Poisson process. And then when the other one, the event of the second one, you put an arrow to the left, you get something like this. And the third one, you put a cookie. And now, if you want to know the value of h at a given point in space-time, so if you want to know the value here, what you do is you just go down, you go back down towards time 0, but you always follow the arrows, and then you count how many cookies you picked up, and the value here is just the value here plus the number of cookies that you've picked up along the way. Okay? And so now clearly this graphical construction sort of clear that that has a scaling limit, right? Because sort of these trajectories simply become Brownian motions that run backwards in time, and they coalesce, right? In the sense that, for example, if I take this guy, well, no, so here that one actually doesn't really coalesce with anything. But if so if I look at this backward trajectory, so it does this. So if I look at the one starting from here, for example, well, it follows this arrow, and then here it gets to the same point. So from now on, it just does exactly the same thing as the other one, right? So if I take the scaling limit of this picture, what do I see? So I just get, so in the scaling limit, if I want to sort of figure out the joint distribution, if you want, of the scaling limit for k different space-time points, what do I do? So I take a Brownian motion running backwards, starting from each of these points, except that these Brownian motions coalesce when they meet. Right? So that one does this, and so maybe that one meets it here. And then what you do is to each of these segments, right? So now you have a tree structure, and so these branches of this tree, they have height. So you just look at the height in time. You don't care about how far they go in space. So each branch has a length, which is just the time difference between the end and the beginning of the branch. And so now to each of the branch, you assign a normal random variable with variance equal to its length, to the length of the branch. And then what you do is the value here is simply the sum of those random variables that are sort of on the branches that you traverse when you go down this tree structure, or this forest structure, down to time 0, right? So the value here would be the value at the origin plus this random variable plus this one, right? The value here would be the value at the origin plus this random variable plus this one, etc. Okay? So that gives you, if you want, the k space-time point distribution of the scaling limit. Right? So you have an immediate characterization of this guy. And of course, that 1, 1, 2 scaling sort of falls out of that, right? Because the ratio between space and time is clearly 1 and 2 in order to get Brownian motions from your random walk. And then the vertical scaling is sort of, again, the square root of the time scaling, because you essentially have like vertical Brownian motions that run along these branches, and so you get kind of a square root of the square. So the vertical scaling is the same as the horizontal scaling. Okay, so you can immediately read off these scaling exponents 1, 1, 2 from that picture, and you immediately get sort of the joint distribution at k points, k space-time points. And so then you can ask yourself, can you prove nice properties of that? So what are the properties of that process, right? So first, this picture here just gives you k-point distributions. You'd want to know, can I realize it as a random variable in some kind of function space, or in some sort of, is it an actual process, or is it just a collection of random variables at every space-time point? From the simulation, it's kind of clear that it wouldn't be a continuous process. It seems to have jumps, right? So you can ask yourself, can you maybe it's a continuous process in time with values in some Cadillac space, like Skorohod space. Actually, it's just about not, because the problem is that when you have, if you have a Cadillac function that, say, looks like this, and then these discontinuities move, and so what happens, I don't know if you remember in the simulation, so these towers, sometimes they disappear. So if you want, sometimes these discontinuities, they hit each other, and then the corresponding tower here, just vanishes, if you want, because the two sides have collapsed. And an event like this is not continuous in Skorohod, in the space of Cadillac functions, okay? So if you kind of think about what the topology does, this is not a continuous event. But so you can show that what you get, you can realize it as a right continuous trajectory, if you want, with values in the space of Cadillac functions, or you can realize it as a continuous trajectory in some LP log space or something like that, right? So you can kind of extract pathwise information from that. So then the other thing you can ask yourself is, what do I actually see at fixed time, right? So if I look at this picture at fixed time, then I see a process in space which has this 1-1 scaling. And so in both previous examples, what I got was a process with a 1-2 scaling, which was essentially the only process just of one variable which has these properties and has the 1-2 scaling, namely Brownian motion. Okay, so Brownian motion is the only process which is Markov, stationary, vertically shift invariant, and has the scaling exponent 2 or a half, so depending on how you count. So then I think, well, there is a unique process also which is Markov, stationary, vertically shift invariant, and has scaling exponent 1, which is the Cauchy process. And the Cauchy process is purely discontinuous. So you can ask yourself, if I freeze that picture in time and I look at it as a function of space, do I see a Cauchy process? Or do I see something that at least locally somehow looks like a Cauchy process? And so, well, so you can prove, so one thing which is not difficult to prove is that if you look at sort of h of x minus h of y divided by x minus y, then this converges in law, if as x goes to y, to a Cauchy random variable. And this is really, so why is that the case? Well, you see, if you take two nearby points, so say this one and this one, and so here you have something like that. So what's the difference between the two values, right? So the value here is the value here plus sort of this random variable plus that one plus that one. The one here is that. So the difference between the two values is just the sum of this random variable and that one, and they are kind of the same. So it's basically just a Gaussian with variance given by the first hitting time of a Brownian motion, of two Brownian motions, the first time they hit. But that's a stable random variable, and a Gaussian with variance of an independent stable one is a Cauchy random variable. Okay, so this is actually basically equal to a Cauchy random variable with parameter 1 if you normalize it correctly like this. So that certainly goes in the direction that this could be a Cauchy process. But of course, it's actually not going to be one because there's no reason to expect these increments to be independent. Because you see, what does it mean for an increment to be big? If such an increment is big, it basically means, since Gaussians, they have very, very light tails, right? So they are just not going to be big. So the only reason why this could be big is because that coalescence time was large. And now, what does it mean? So if this coalescence time is large, it means that these two Brownian motions, they have to avoid each other for quite a long time, right? So you have to see a picture a bit like what I drew here, where one of them kind of shoots off in one direction, the other one shoots off in the opposite direction. They avoid each other for quite a long time, and then they come together. But now it means that if I take the next guy here, this Brownian motion will have a hard time avoiding that guy, which kind of shot off in that direction, right? So this is going to be actually coalesced pretty quickly, and so you'd expect this increment to be quite small. Right? And so you don't actually expect these increments to be independent. You'd rather expect that if one of them is big, then the ones nearby are small. So in some sense, these jumps should kind of repel each other. Okay, and so this you can prove in the sense that you can prove a theorem which says that locally, so if you look at the law of this guy on 0, 1, then that law is singular with respect to the law of the Cauchy process. Okay, but otherwise, you can also prove that it has, if you want, most of the natural properties are the same. Okay, so if you ask things like, well, for example, it's a pure jump process. It has no continuous part, in the sense that if you remove jumps of size bigger than delta, and then you let delta go to 0, you just end up with a constant. Okay, so in that sense, the process is pure jump, just like the Cauchy process. You can show that it has infinite 1 variation, but finite p variation for every p bigger than 1, just like the Cauchy process. So it has quite a lot of properties that are in common with that of the Cauchy process. So it has a realization which is Cadillac, just like the Cauchy process, and so on. So now, one of the sort of striking features of this process was that you had these discontinuities, right, that kind of move around. So you can ask yourself, can you give a sort of can one give some kind of description of what these discontinuities do, right? So first, what actually creates a discontinuity? So a discontinuity here corresponds to basically a point in which you have somehow two Brownian motions that come out sort of simultaneously. And so then in this picture, right, so if you imagine that here, if I approach this point to this one, so if you imagine that very close to here I have a Brownian motion that sort of avoids that one for quite a long time, right? And so if in the limit you still have sort of one of them going to the right, one of them going to the left, then that would create a discontinuity at that point, right? With the sort of left limit being the one you get by following the left branch, and the right limit being the one that you get by following the right branch, right? And so these discontinuities, therefore, so they correspond to points in that picture of these coalescing Brownian motions where you have sort of two Brownian motions that exit the same point. Now, of course, if you just take a deterministic point, this doesn't happen, right? So if you just take a point and if you try to start two independent Brownian motions from the same point, they're going to instantly coalesce, right? And so you would never see that. But the point here is that in this picture, you simultaneously start coalescing backwards Brownian motion at every single point in this plane, right? So you have these uncountably many points where you start these coalescing Brownian motions simultaneously at every point. And so that's called the Brownian web. Okay, so if you want, the process that we get here is essentially a Brownian web over which we then superimposed some kind of branching Brownian motion that sort of branches according to the tree structure of the Brownian web. Right? So these coalescence, sort of these discontinuity points, they correspond to points in the Brownian web where you have more than one backwards Brownian motion emanating from the same point. And so these points exist. So as a matter of fact, so the Brownian web is sort of quite well studied. there exists, there's a full characterization of all the types of points that show up. And so in the case of the Brownian web has the property, right? So you take every point in space-time and you have coalescing Brownian motions running backwards. It turns out that there's a dual, so Brownian webs, they always come with two dual Brownian webs, in the sense that at every point there exists exactly one trajectory that goes forward in time, which has the property that it does not cross any of the trajectories that go backwards in time. Okay? So you see, so imagine the picture you have. So at every point here, you have these trajectories going backwards in time that emanate from every point, okay, and they coalesce. And then simultaneously at every point, you can actually look at trajectories going forward in time in such a way that they don't cross the backwards one. Right? So the sort of picture that you can have in mind, so that's one way of constructing the Brownian web, is you take a copy of Z2 that's rotated by 45 degrees, and at every point you draw an arrow that goes backwards, and you just choose one of the two possible directions at random. Right, so something like this. So now this would create a Brownian web, right, if you just follow the arrows and you take the scaling limit of this object. But then you clearly also have a dual Brownian web on the dual lattice by saying at every point there's going to be exactly one of the two directions that I can go which doesn't cross a white arrow. Right? So here I have to go like that, 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 and so on. Right? So there's exactly one, oops. Right, so I get something like this. And, you know, at least here it's sort of clear that the purple picture is actually just the same as the white picture in law, right? I mean, of course, each of them is a function of the other one, but in law they are kind of the same. They're just flipped around, right? And so in the scaling limit, this picture sort of survives. So whenever you have a Brownian web, you also have a dual Brownian web that goes in the opposite direction, and that is actually a function of the original one, and which has these properties that the trajectories never cross. Okay? And so, so now in this picture you have, there exists basically 7 types of points in the Brownian web. Right? So 7 types of points. So a typical point just has one trajectory going down and one trajectory going up, right? So on a typical point, well, a normal point, if you want, of the Brownian web is a point where I just have one of these Brownian motions emanating backwards. And therefore, also a typical point of the dual Brownian web is one where I have exactly one trajectory sort of emanating forward of the dual web, right? So that's the typical points. So they have full Lebesgue measure. Okay, so almost every point is of that type. But then there are special points. So for example, there are points like this, which is already what I sort of mentioned here, which are points where you would have 2 trajectories emanating backwards from the same point, and then they correspond to points that are located, if you want, on a trajectory of the dual web. And then you have points where you have 3 trajectories emanating backwards, and sort of that corresponds to a point where you have 2 trajectories in the dual web that coalesce. And then you have, if you want, the duals of these types of points, which is essentially what you get by flipping the picture around and inverting the colors. Right? So you would have this one, where you have, that's points that are on a trajectory of the Brownian web, and where you have 2 points, where you have 2 trajectories of the dual Brownian web emanating from that point. So then you have the dual of that picture, which is this one. So that gives you 5 types of points. And then there is one more type of point, which is something like this, where you have a trajectory, and then you have, if you want, another guy that emanates from the middle of a trajectory somehow. And there's 2 ways in which it can emanate. It can either emanate to the right or to the left. And then the dual guy here is sort of this. And here, well, these are duals of each other. Right? So that's the 7. So there's a theorem which says that, well, these are the only possibilities. Okay, so every single point of the Brownian web is one of these 7 types of points. And so we've seen now that somehow singularity, discontinuities of our process correspond to points where you have more than one backwards trajectory emanating. So it would be like this one, or this one, or possibly one of these 2, okay? And so now you can ask yourself, can you actually track one of these discontinuities sort of from its birth to its death, in the sense that you would want to assign to each discontinuity something like an age, and then you would want to say, well, whenever 2 discontinuities meet, then it becomes only 1, and I view this as sort of the older one eating up the younger one, right? So that the sort of the age of the remaining one is sort of the age of the older one, rather than the age of the younger one. Yes?
In what sense there are only those 7? Somehow these 6 are anyway with probability, with measure 0 somehow.
Well, they are with measure 0.
Maybe some other ones where somehow, you are joining more of them in one point somehow, but they will have even less than 0 probability.
No, but you can really, okay, so in the sense that you can actually realize this Brownian web as an actual random variable in some space of topological spaces, right? So you can view this as a kind of as a topological space where you put distances, and then almost sure, right? So then these kind of notions make sense. So you can actually just look at the topological space that you get. You can look at sort of what type of points that you have, and you make the space compact. So there's a kind of right. So you can. So what you do is you kind of start at countably many, so first on a countable dense set of points, then you look at those trajectories, and then you take a closure of that somehow, right? And then the space that you get, then with probability 1, that space has exactly these 7 types of points, but it will have them, right? In the sense that you can't avoid them if you want your space to be complete, somehow, the space that you get. Okay. So it's in that sense, if you want. Right, in the same way as you can say, well, if you're only given Brownian motion by its sort of 1-point marginals, then there's no time at which it's going to be 0, right? But of course, if you realize it as a continuous trajectory, it will be 0 at some point, right? You can't avoid that, right? So it's in the same sense. Right? Okay, so now I claim that actually you can see, so there's a nice, if you follow, you want the sort of life and death of a singularity, you actually see all of these types of points, of these types of special points, kind of on the way. Because so first, how can a singularity be born, you want, right? So what happens, well, so first I claim that singularities really correspond, so the locations of the singularities really are the trajectories of the dual Brownian web here, right? And so now so of course you'd say, well, in that sense, singularities are born all the time because trajectories of the dual-Brownian web, well, they start from every point in space-time. Yeah? But then, of course, most of these instantly coalesce with some older singularity that's already around somewhere. Right? So how could that be prevented? Right? So if you take a typical point on which you have a sort of purple trajectory emanating, well, you take another point which is just a little bit further back here, there's another trajectory emanating, and that's going to instantly coalesce with this guy. And I can make that probability as high as I want by making these points very close to each other. And in that case, well, just after that coalescence, this singularity is really this one, because that's the older one, right? And so how can I prevent this? So I must have something that kind of shields me from all these other singularities that want to coalesce with me. And basically the only way that that can happen, right, so the only type of points here which provides such a shield is this one. Right? Because what happens here is that you have from the same point, you have kind of 3 forward trajectories emanating at the same time. And so now what happens if you take any of the guy further back, it's going to instantly coalesce, but it's going to instantly coalesce with one of these two. Right? It's never going to coalesce with the middle guy. Right? So the middle guy here is shielded from the past, if you want, by these two sort of protectors that go off from either side. Right? So if you want, that's how singularities get born in this picture. Right? So it's these special points here that allow you, if you want, to create a new discontinuity in this space-time process. But so now if you follow that, well, of course, at some point, this guy is going to die. Right? So how is it going to die? So it's precisely the protectors that allowed it to be born in the first place that actually are going to kill it in the end. Right? Because, anything else, right? So any other guy here, any singularity that gets born somewhere here, well, okay, so it's going to coalesce with that guy, but all the singularities born in these regions, they are all younger. Right? So if the oldest guy in this region is this guy here. And so the only way that this guy would ever die is because it coalesces actually with one of the two guys that protected it. Right? Because now this guy, of course, is older because this guy has already, coalesced with some other guy from its past. And so the age of this guy now is at least this, right? So here it's going to, so you're going to see a special point of this type, right, where you have two of the forward trajectories coalescing. And so that's how these singularities die. But then you can ask yourself, during its lifetime, in some sense, what did it eat up? Right? So what is sort of like the region of all those singularities that actually got eaten up by this singularity here during its lifetime? Right? So there's going to be some region in here which separates those singularities that coalesce with the guy to the right from those singularities that coalesce with this guy here, right? Now, so that region, what does it correspond to? Well, it corresponds precisely to the trajectory in the backwards, right? So in the backwards Brownian web, I have, right? So this is an event of this type. So in particular, I have a middle trajectory going backwards here, right? And this trajectory here, I know that it cannot cross any of the purple trajectories. So the only way it ever exits this region, since it's not allowed to cross either of these purple trajectories, is to actually exit exactly through that point, right? So the trajectory, backwards trajectory that is created here in the middle has to be exactly the same as the one that exits that point, which of corresponds to one of these two trajectories here. And so any guy which is created to the right of that backwards trajectory is not allowed to cross it, so has to coalesce with this guy. And any guy that's created to the left has to actually coalesce with that one. Right? So these backwards trajectories, so that's these guys here, they precisely provide the boundary, right, between the region, you know, if you want the basin of attraction somehow of that discontinuity, right? So you have this backward trajectory, and then there's the other one. There's another one here which does exactly the same thing, right? And which provides the other boundary. And now what about these two special points? Well, what happens is that these backward trajectories, they can actually bounce off this trajectory here. So they don't necessarily stay away from it. So they're not allowed to cross it, but they're allowed to bounce off it. Okay? And so a point like this, where the backwards trajectory bounces off the corresponding forward trajectory, so that's exactly these special points. Right, so that special point is the one where this backward trajectory bounces off, if you want the lifeline of the singularity, and the other one is the one where that backwards trajectory sort of bounces off the lifeline of that singularity. Okay, so you have this kind of nice picture that sort of shows the different sort of associates, if you want, the different special points, and of course that's just sort of the typical, right? So the typical point in the life of the singularity is sort of a typical point on that line, so that's a point of that type. Right, so all these special points, they just correspond to sort of different events that you can kind of read off from the picture, right? So different events in the life of these singularities for that process. Okay, so I think, okay, so so what we're interested in now, so now we have good description of that guy, right? So what you would like to know is there, you know, an analog of the KPZ equation? So what are sort of the heteroclitic orbits that connect that guy to these? And do they also have this sort of universality in the sense that that guy was supposed to be the only guy that connects these two? And so what we think, okay, so first this guy seems to be less stable than any of these two, in the sense that you can perturb it in a way that converges either to this guy or to this guy. So generically to this guy, but then there are perturbations you can find that make it converge to Edwards-Wilkinson. So it's in that sense, it's sort of less stable than either of the two. And at least here, since both of these have very explicit description, you have a hope of being able to find a very explicit description of whatever connects the two. And so this, we think that we have a description, so that's still conjecture if you want, but we have a conjectured description of what links these two, and here it's not just one heteroclinic trajectory. So there's a whole infinite dimensional family of them, actually, which is really related to some coalescence, and they are sort of parametrized by the measure that shows up in these coalescence somehow. So every measure gives you a different heteroclinic orbit that connects this guy. So in that sense, this one sort of, in this RG picture, it sort of behaves quite differently from it. So in a way, you can't think of perturbations being polynomials or something and then doing some kind of, you know, just hand-waving analysis that tells you which ones are stable, which ones are unstable, as you can do here, and that sort of tells you that there should be only one unstable direction. So here you can't do a picture like that. It looks like there are actually infinitely many unstable directions in that sense. Okay. I think I should stop here. Thank you very much.
So are there any real-life applications of these different fixed points? For example, if you look at coastlines, or I don't know what. I mean, where do these things appear in real life?
Yeah, well, okay, so that one, you see it, so there's the, okay, so the one real experiment that I know of where, you know, so if the measurements are sufficiently clean that you can really match it up with the theory and it matches, is in these liquid crystals. So there's actually some liquid crystal, the 2D liquid crystal, which comes in two phases, and then you can sort of zap with a laser beam, and then it sort of flips to one phase, and then you see that one. So that one really shows up in that there very naturally. So generically, you would kind of right. This is sort of the generic one in a way. Now, so this one, you can sort of tell yourself a story about, you know, life forms on a coastline where these things are actually genetic, you know, ancestry lines, if you want, and then space is they only move in a one-dimensional space, but then there's the sort of the time evolution is the sort of genealogical time evolution, and then you can sort of tell yourself a story that would correspond to this process here, but whether that's really real, how realistic that is, I wouldn't sort of.
So you have this scaling symmetries actually for all three fixed points, but is there any of them where you have an enhanced kind of conformal-ish symmetry?
Well, okay, so for KPZ, you have a kind of Galilean symmetry as well. Right? So here there's a more subtle symmetry where you kind of change, right, where you kind of shift it. In a way, it sort of corresponds to, like, if you add a drift to it, then you can sort of compensate it by shifting the process. So if you add a drift in the sense that you just change x into x minus constant times t, so you kind of shift the whole process like that, then that's actually the same as shifting it vertically. So there's an extra symmetry like that. But otherwise, I mean, space and time really play completely different roles, right? So there's certainly no rotation.
And the new fixed point either, there's no...
No, so that one has the same, okay, so that one has obviously x goes to minus x, and less obviously h goes to minus h, well, sort of obviously in the continuum picture and not obviously in the discrete picture. Right, so it has these two symmetries, and it definitely does not have the t goes to minus t, and so, I mean, that's the only two symmetries that I know of for that process. Right.
So in quantum field theory, there's this landscape usually refers to, you know, quantum field theory RG flows connecting conformal fixed point, and there is a very clear picture that each fixed point is characterized by a set of anomalous, by a set of dimensions, and you know exactly which corresponds to which ones are the relevant ones corresponding to a perturbation. Is there a similar general picture in this kind of this nature in this business?
No, not that I know. I mean, in the sense that there's certainly no theorem that kind of characterizes, right? So, I mean, that would be a fantastic probability theorem, which would be a theorem that says, you know, here are all the, so you want the additional property, which is scale invariance.
Well, I understand you don't have that here, but I mean, you have something similar.
And so, well, so here these processes are scale invariant, so that's sort of the, right, with different exponents. Yeah.
What I mean is, like, you have, like, in the tree-critical easing model, you have a field of dimension 1/10, and then you just know this corresponds to a relevant perturbation. You just look at it. So to classify where you can go.
I think here you don't even have a classification of where you can start from. So, but yeah, so I mean, of course you can do, so for that guy, right, so for the Gaussian one, you can do this formal calculation that tells you where you can go, right, which just says, well, this guy is described by an SPD, right, that's just the stochastic heat equation, it's just dth dx square h plus white noise, and then you ask yourself, well, you can add any polynomial term, so you take a polynomial in h and sort of dxh, say, and then you can do
general conformal fixed point. You just have fields. There are no basic fields. You just have fields of a certain dimension. Is there something?
No, not that. No, I'm not sure what would be the analog here.
That's good stuff.
If you slightly generalize the discrete model by losing the nearest neighbor property, so for example, 1/5, 1/5, 1/5, 1/5. On the discrete level, at least you lose this duality picture.
Right, because it means that things could actually cross then, right?
I think in the scaling limit it still is the case, so would you expect the same?
You would probably expect the same. Because they would, right, because these lines they could actually cross, but then once they get, not for long, because they would still actually end up coalescing sort of pretty quickly, and so you would actually, I would expect the same scaling limit.
So there is a fascinating analogy, because in 2D critical phenomena, you could say that there also some theory which has infinitely many relevant perturbation, which is just GFF.
Right.
And from that theory, you can flow to critical easing, but also to infinitely many other fixed points. So now it seems like you are discovering this analog of GFF, which has infinitely many relevant directions, this Brownian castle.
No, but they all flow to Edwards Wilkinson.
Is it obvious that you cannot
so the
fiddle
ones
with them a little bit, and if you fine tune them in a very special way, then actually you will flow somewhere else to some more fixed points? Because you have infinitely many, there's a lot of room to play.
Yeah, but those we have you have an explicit description of what they do, and so you can just you see that it just converges to that guy. There doesn't seem to be much room, but and then if you just take a generic perturbation, at least numerically, so if you do, so if you do the thing where where you actually, if you did the finite temperature one somehow, right, where you take this, you bias by the height of the process. Then at least numerically it seems to be instantly in the KPZ universality class.
Alex.
So for the KPZ fixed point, I suppose if you replace the Laplacian by a fractional Laplacian, then you can do an epsilon expansion when you bring it close to the Edwards-Wilkinson fixed point at distance epsilon. But is there something similar one could do for this new fixed point, you think?
Well, this doesn't really have a good description as something like an SPD or something, right? I mean, if you want the closest that it would kind of correspond to something like this, like eta times d. It's sort of like a transport. You'd have like a random transport term where both of these are sort of independent, right? So one of them, this kind of corresponds to the coalescing Brownian motion, and this corresponds to the sort of vertical fluctuations you put on top. And it's sort of, you would expect things like that where these are just sort of sufficiently mixing random fields to converge to that fixed point. Now, as soon as you add a small Laplacian to this, for example, then you seem to be back to Edwards-Wilkinson somehow. And so, I don't know. It's not.
I mean, in this coalescence
Not
picture,
clear.
couldn't you just allow longer arrows, kind of to make this kind of a long range, which would be kind of somewhat like making a fractional Laplacian?
You mean in such a way that like these backward characteristics would be something like Levy processes
Yes,
rather than
yeah.
Brownian motions also. Yeah, but then they would really jump over each other, right? And they would genuinely jump over each other, so that would be quite different somehow. So it's not clear.
You would lose this symmetry somehow of the pink sink or whatever. It's not pink, it's violet.
Oh, right, so like this duality, yes, you would definitely lose that duality, yeah. But you would probably also just lose the whole thing. I mean, I suspect that you might just end up with like a fractional heat equation or something like that.
I think we should draw it to a close now. Thank you very much.